Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. You know, I teach very slowly for your better understanding, but due to time and space constraints, I am teaching a little bit faster. Please bear with me. And welcome to this fifth clip. In the fourth clip, we have discussed Lebesgue numbers associated with open covers of metric spaces, and we have seen that Lebesgue number for an open cover of a metric space may or may not exist, and then we have proved that every open cover of a sequentially compact metric space has Lebesgue number. Today in this clip I bring to you another new concept, which is total boundedness. And to define total boundedness of a subset of a metric space, we need another concept, epsilon net for a subset of a metric space. So let's begin with epsilon net. Okay, so let epsilon be any positive real number and A be any subset of a metric space HD. Okay, a finite subset, mind it, a finite subset in, say, x1 x2 ... xn of A is called an epsilon net for A if the open balls centered at those points of n, each of radius epsilon, cover whole x. That is, if the union of this open ball BD xi epsilon I runs from 1 to n, this union contains E. Okay, that is if this is a metric space and if this is a subset of this metric space, then an epsilon net for this A is a finite subset consisting finite number of points of A, say x1, x2, x3, so on. If the open balls centered at x1, x2, x3 in this way, each of radius epsilon can cover whole A. Now, by using this concept of epsilon net, let's define a new kind of boundedness of a subset of a metric space. Okay, which is known as total boundedness. So total boundedness. Okay, a subset A of a metric space, of course, of a metric space XD is called totally bounded, is called totally bounded if epsilon net for this subset A exists for every epsilon greater than 0. What does it mean? It means if this is a metric space xt and if this is a subset of xt, okay, and if we take any epsilon greater than 0, then for this epsilon we should have finite number of points of A, so that the open balls centered at all those points, finite number of points of A, each of radius epsilon can cover whole A. Mind it, this must hold for every epsilon greater than 0. Okay, sometimes it is seen that for some epsilon there are finite number of open balls centered at finite number of points of A, each having radius epsilon can cover A, but if we reduce it, if we consider another number less than that epsilon, another positive number less than this epsilon, then it is seen that there is no finite number of points for which the open ball centered at those points having radius that quantity less than epsilon cannot cover A. Okay, but I will discuss it later on. Before that, let's establish a relation between this new kind of boundedness, total boundedness, with the classical boundedness of a subset of a metric space. You know, a subset, so this is a metric space xt. You know, a subset A is called bounded in this metric space if there exists an open ball which contains this A entirely. Okay, that is, if A can be placed within an open ball in this metric space, then this A is called bounded subset of this metric space. And this is not new. Actually, you know, in BSc, a subset A of R is called bounded if there exists a real number m, so that mod of A less than m for all A in capital A. Now we can write it in this way: mod of 0 minus A less than m for all A in capital A. And you know, this is the this can be written as this d0 A less than m. This is the standard metric on R. There is dxy equal to mod of x minus y for all xy in R. So this is nothing but d0 A for all A in capital A. And this means this A is a member of this open ball BD centered at this 0 having radius m for all A in capital A. And what does it mean? That is, every element of capital A is also an element of this. So this implies A contained in BD0M. So A is placed within an open ball. Okay, so we see that if A is bounded, then A is contained within an open ball. And just if we go in reverse way, you will find that if A is placed within open ball, this kind of open ball, then we can write in this way, that is A will be bounded in classical sense. Okay, so in case of R with usual metric, that is in BSC also, A subset A is bounded, a subset A of R is bounded if A can be placed within an open ball. Okay, this definition in case of metric space, a definition of bounded subset is derived from this. Okay, so a subset A of a metric space is bounded if it can be placed within an open ball or a closed ball. If we consider here less or equal to, then we will get a closed ball. Fine. So let's establish a relation between boundedness and total boundedness. Okay, so relation between boundedness and total boundedness. Okay, fine. Okay, let me change the page. Okay. Actually, every totally bounded subset, every totally bounded subset of a metric space is bounded. Every totally bounded subset of a metric space is bounded. Okay, let's prove it. For let A be totally bounded. A be totally bounded subset. Totally bounded subset of a metric space XT. So totally bounded, so epsilon net for A exists for every epsilon greater than 0. So epsilon net for epsilon equal to 1 also exists. Okay, so let this set x1 x2 dot xn, this b and 1 net, epsilon equal to 1, be 1 net of A. Okay, so then by definition of epsilon net, the open balls centered at those points each of radius 1 will cover A. That is the union of this open ball with dxi1 I equal to 1 to n will contain whole A. Now let x and y be any two elements of A. So they are in A, so they are in this union. So x will be a member of some participant to this union, y also. Okay, so and let x in BD xi1 and y in BD xj1. Okay, for some I j, of course they are within 1 to n, because epsilon net is this x1 to xn. Okay, fine. Now let's calculate the distance between x and y. Okay, now dxy, this is less or equal to dx by triangle inequality, dx xi plus d xiy If we use triangle inequality once more, then we will get dxxi plus here dxi xj plus dxjy. Okay, now let's keep this in the beginning, xi xj plus, now what is this, dxxi, x in this open ball, okay, center dot xi, radius 1. So the distance between the center and this point within it will be less than its radius, that is dxxi less than 1. Similarly dxjy less than 1. So this is less than 1, this is also less than 1, so less than 2. Let's call it m. Okay, we'll use it later on. Okay, now without loss of generality, let j less than I. Then we can reach j from I in this way, I plus 1, I plus 2, I plus 3. Okay, in this way one can reach to j. So let this I plus k equal to j, and then actually we will calculate this, we will calculate an upper bound of this. Okay, then d xi xj, this is just if we use triangle inequality repeatedly, then we will get dxi xi plus 1 plus d xi plus 1 xi plus 2 plus dot, in this way, plus at the end, just before reaching to j, we are getting j minus 1 xj, isn't it? And this is a portion of this finite series, dx1 x2 plus d x2 x3 plus plus d x n minus 1 xn. Okay, if I equal to say 2 and j equal to 5, so from this to up to x dx4 dx5. Okay, so this is a portion, fine, of this. Now every term of this finite series is finite quantity, finite real number, and there are finitely many terms, so it will give you a finite quantity. Okay, so let it be n, say, and call it s, so from m and s, from m and s we are getting, m is this, the dxy less than, so dxy less than d xi xj, dxi xj lesser equal to n, so lesser equal to n, no, not less than, just less than n plus 2, and it holds for all xy in a. Look at this, xy arbitrarily taken from a. So this holds for all xy in a, and from this we can write y belongs to b dx n plus 2 for all y in a. And from this we see that every point of a is also a point of this, so a subset of b dx n plus 2. So a can be placed within an open ball. So by the definition of classical definition of boundedness, so A is bounded. A is bounded. So every totally bounded subset of a metric space is bounded, isn't it? We have considered A is totally bounded, and we see that it is bounded. Fine, but the converse is not true. The converse is not true. The converse is not true. That is, a bounded subset of a metric space may fail to be totally bounded. How? Okay, so let me write. But a bounded subset of a metric space may fail to be totally bounded. For that is, boundedness may not imply total boundedness, may not imply. So we will show it by some example. Let me consider a very simple example. We will consider an infinite discrete metric space. That is a discrete metric space where the underlying set is infinite. For let X be an infinite subset, infinite set, and D the discrete metric, that is dxy is 0 if x equal to y, and it is 1 if x not equal to y. Fine. And then this is discrete metric space, because if we consider the open balls, say BD centered at any point x having radius r, so by definition this is the collection of all points of the space x such that dxy is less than r. Now, if I already discussed in the first semester, if r is greater than 0 and less or equal to 1, then what will happen? If we put even 1, then also dxy less than 1. But dxy, for dxy there are only two options, 0 and 1. So if r1, then dxy must be 0 because it is less than 1. And dxy 0 means y equal to x. Okay, so all those y will be x. So we will get just singleton x. The center will be only the member of this open ball. If we take radius less or equal to 1 and greater than 0, of course, because if we take 0 or less than 0, if we put 0, then dxy become negative and it is not possible. So no y will come here, no point will be there, so it will be empty set. Okay, and if we put here negative, then it is also negative, then same, this is empty. That's why we take radius always greater than 0, and this is also the reason behind taking epsilon greater than 0 always. As you have seen the BSc, always we take for any epsilon greater than 0. This is the reason. Okay, now if r greater than 1, then what will happen? R greater than 1, so this may be 1 or 0. Okay, if this is 1, then y, then here y not equal to x, that is y may be anything other than x, other than a small x. Okay, so all the elements of x will be there other than y, other than x, isn't it? And when it is 0, then y will be x. So ultimately we are getting all points of x, that is we will get whole x. Fine. Okay, so x can be written as bd small x 2, say 2, we are taking radius greater than 1, so it will be whole x. So x intentionally you can write subset because equal, so x is also bounded, so any subset of x is bounded. Okay, so this implies any subset of this matrix for HT is bounded. Okay, now let A be any infinite subset, of this HT. Then as simple as that, A is bounded, but my claim is A is not totally bounded. This is my claim. The claim is A is not totally bounded. Okay, for if possible let A be totally bounded. Then for epsilon equal to half, A has an epsilon net. Okay, for epsilon equal to half also. For epsilon equal to for any epsilon greater than 0, A should have epsilon net, because we have considered that A is totally bounded, and I am considering just one case, epsilon equal to half. Okay, A has an epsilon net, and let it be this x1 x2 dot xk. Okay, then by the definition of epsilon net, this union bd xi, this epsilon, that is half, I equal to 1 to k here, it will contain whole A. Okay, now bd xi half, the radius is half. Look at this, the radius is half, less than 1, so it will be a singleton. It will be a singleton, and that singleton is the center of the open ball. So all open balls participating in this union are singleton containing the corresponding centers. Okay, so this is nothing but the union of xi, I equal to 1 to k, and it contains A. Now what is this? If you take this, you will get just x1 x2, this epsilon net dot xk, and it contains A. And this implies, since this is finite, so A subset, so A is finite. This implies A is finite, but our A is infinite subset of this, isn't it? A is finite, which contradicts infiniteness of A. Okay, so if we assume that A is totally bounded, then we arrive at a contradiction. hence A is not totally bounded. So A is not totally bounded. Fine. Though A is bounded. So boundedness may not imply total boundedness. Okay. Now, by using this total boundedness together with completeness of a metric space, you know completeness of a metric space, most probably in BSc you have studied all those things, isn't it? Completeness, you know. Okay, let me recall a little bit. Let XD be a metric space. Okay, it is called complete. It is called complete if any Cauchy sequence, in this metric space is convergent. Okay, if every Cauchy sequence in this metric space is convergent, then this metric space is called complete. Okay. Now I should mention one of the interesting property of Cauchy sequence. Okay, you know definition of Cauchy sequence, of course. Okay, I am not going to discuss this. You know Cauchy sequence. So a metric space is complete if every Cauchy sequence therein is convergent. So I just want to mention an interesting property of Cauchy sequence. Okay, you know a sequence in a metric space is convergent if and only if every subsequence of it is convergent and converges to a particular point. Okay, and we can say in some sophisticated way, which is equivalent to that a sequence xn in a metric space HD is convergent if and only if that is at least two subsequences of it is convergent. One is of the form x to n, okay, and another is x to n plus 1. That is the even term subsequence and the subsequence of odd terms. Okay, if both converges to a same point, then this will converge to that point, and conversely. Okay, so for an ordinary sequence, for the convergence of an ordinary sequence, we should check at least convergence of two subsequences. But to check whether a Cauchy sequence is convergent or not, it is sufficient to check whether a subsequence of it is convergent or not. If one subsequence of this Cauchy sequence is convergent, then this Cauchy sequence will be convergent. Okay, if any one subsequence of a Cauchy sequence is convergent, then this Cauchy sequence will be convergent. Very easy, you can check. Okay, we are in a metric space, so and all those things already studied in BSc, so just 2 or 3 lines will be required to prove it. Okay, so this is an advantage for checking whether a Cauchy sequence is convergent or not, just if one can show that there is a subsequence which is convergent. Okay, then that Cauchy sequence will be convergent. I will use this fact. Okay, Fine. Where I will use? Now I am going to characterize sequential compactness. That is when a metric space will be sequentially compact. Okay. So by the help of this total boundedness discussed few minutes back and this completeness of a metric space. Okay. By the help of these two, we will characterize sequential compactness. Okay. Fine. Okay. So this is another result. Important result. A metric space HD is sequentially compact if and only if it is complete and totally bounded. It is complete and totally bounded if and only if, mind it. That is, if a metric space is sequentially compact, then it will be complete as well as totally bounded. And if a metric space is complete as well as totally bounded, then that metric space must be sequentially compact. Okay. So let's prove this result. Okay. So let me sketch the proof. So let XD be a sequentially compact metric space. Okay. Sequentially compact metric space. First we show completeness of this. Okay. Okay, so completeness of AXT I am going to show, and it is very easy. Let xn be any Cauchy sequence in AXT. We will show it is convergent, isn't it? So let this be a Cauchy sequence in AXT. Since XD is sequentially compact, so by definition of sequential compact space, just recall every sequence in this has a convergent subsequence. Since this, so this sequence, so xn has a convergent subsequence. Okay. Since xn is Cauchy sequence and it has a convergent subsequence, so by the result just discussed, okay, that a Cauchy sequence, to check a Cauchy sequence, it is sufficient to check whether it has a convergent subsequence or not. If a Cauchy sequence has just one convergent subsequence, then that Cauchy sequence must be convergent, isn't it? So since this is a Cauchy sequence and it has a convergent subsequence, so this is convergent. This is convergent in this metric space XD. So we have started with any Cauchy sequence in XD and we see that it is convergent in XD. Okay, so every Cauchy sequence in XD is convergent. So XD is complete. So XD is complete. Fine. Okay. So if the metric space XD is sequentially compact, then it is complete. Now let's show total boundedness of this metric space by using sequential compactness of it. Okay. So total boundedness. Okay. Let me prove it by contradiction. That is, we'll assume that the matrix space XD, though it is sequentially compact, but it is not totally bounded, and ultimately we'll get a contradiction. So it must be totally bounded. Okay, totally bounded. So let XD be sequentially compact. Okay, if possible, let this matrix space XD be not totally bounded. Not totally bounded. Not totally bounded. What does it mean? That is, when we say this is totally bounded, if, look at this, here A is whole X, okay? We have defined total boundedness of a subset of a metric space. The subset, so X is also a subset of it, okay? So this X is totally bounded if epsilon net exists for every epsilon, but here it is not totally bounded. So there must be an epsilon greater than 0, isn't it? There must be an epsilon greater than 0 for which there is no epsilon net of it, isn't it? Fine. So this be not totally bounded. Then there exists epsilon greater than 0 such that this X has no epsilon net. No epsilon net. What does it mean? Epsilon net means this is a finite subset of X, so that the open balls centered at those finite number of points, each having radius epsilon, cover whole X. Their union is whole X. But here X has no epsilon net, so we will not find finite number of open balls each having radius epsilon that can cover whole X, isn't it? Okay, this is the main point. This is the heart of the proof. Okay, fine. So finite number of open balls, each of radius epsilon cannot cover X. Okay, cannot cover X. So if we take so for any X in capital X, or call it x1, for any x1 in capital X, actually we are going to construct a sequence in X, okay, because we have considered XD is sequentially compact. Okay, somehow we will construct a sequence in XD and we will show that it has no convergence of sequence, okay, and we will arrive at a contradiction, okay, and then we will declare that this is not true, that XD not totally bounded, it is not true. It means it is totally bounded and we will achieve the goal. Fine. So that's why I am denoting the point, any point x1 of capital. I am taking a point and I am naming this point x1. Okay, for any x in this, so this BD x1 epsilon will not cover X, because I have written here that finite number of open balls, each of radius epsilon, cannot cover X. This is finite, just one open ball, it cannot cover X, so it is a proper subset of X. So there is a point in X, not in this, and call it x2. Okay, let x2 in X minus this BD x1 epsilon. Fine. Again this BD x1 epsilon union BD x2 epsilon. We got 2 points, x1 and x2. So consider two open balls centered at x1 and x2, each of radius epsilon. So here also finite union and open balls, so it cannot cover x. Okay, it is written here, it cannot cover x. Finite number of open balls, each of radius epsilon, cannot cover x. Okay, mind it, remember it. Okay, so this is finite number of open balls, so they cannot cover x, so same thing, so it will be proper set of x. So there exists a point in x, not in this union, neither in this nor in this. Okay, so there exists a point, say x3 x minus this union BD x1 epsilon union BD x2 epsilon. Okay, and in this way, if we continue this, you can use mathematical induction, but I am not going to this. Okay, so in this way one will get a sequence, xn. In this way, x1 x2 x3 x4. In this way one will get a sequence xn in xd such that, now very easy, here x2, look at this, x2 not in this. What does it mean? It means, let me write this, it will be more visible, x2 not in BD x1 epsilon. So D x1 x2 cannot be less than epsilon, because if it is less than epsilon, then x2 will be in this, but x2 not in this. So D x1 x2 will be greater equal to epsilon, cannot be less than epsilon, so greater equal to epsilon. Now come to this point. Okay, come to this line, x3 not in this union, so x3 not in this, also not in this, so x3 not in BD x1 epsilon means D x1 x3 greater equal to epsilon, x3 not in BD x2 epsilon means D x2 x3 not less than epsilon, that is greater equal to epsilon. So if we look up to x3, that is x1 x2 x3, if we confine ourselves within these three terms of the sequence, we see that any distance between any two terms, x1 x2 x1 x3 x2 x3, isn't it? Is there anything more? Obviously no, because there are three elements, we have to take two out of these three, and there is only three ways. Okay, and this the three ways, and in all cases we see that greater equal to epsilon. Okay, so we can write in this way, that in this way one will get a sequence xn in xd such that D xm xn is greater equal to epsilon for all mn in the set of natural number. Okay, fine. Now if we take a subsequence of it, the same thing will happen, isn't it? Okay, so let x n k, okay, be any subsequence, any subsequence of this sequence xn, then what will happen? Same thing. Then what is happening here? Then d x n k and d x n l also same thing. This will be greater or equal to epsilon, okay, for all kl in n. Okay, one thing should I should mention, k not equal to l here also m not equal to n, because if m and n is same, then it will be 0. It is not possible. Okay, fine. So d x n k x n l greater or equal to epsilon for all k l. So from this we can say this subsequence cannot be convergent. Why? Okay, so the claim is this subsequence x and k cannot be convergent, cannot be a convergent subsequence. Why? The why is this. Okay, again, if possible, let this subsequence x and k converges to x of this metric space xt. Okay. Now consider open ball this b d x epsilon by 2. Okay, x is here. Okay, then this open ball can contain, then this b dx epsilon by 2 can contain at most one term of this subsequence x n k. But if I will prove this, okay, but if it converges to x, since this is an open ball centered at x, after some step all the terms of this sequence must be contained within this. Okay, but we will see that this open ball can contain at most one member only. Okay, so this is not converged to x. Okay, so let me show that this cannot this can contain at most one term of this, because if, okay, because let x n k and x n l both are in b dx epsilon by 2, then what will happen? Then d x n k x n l is less or equal to d x n, just triangle inequality, dx n k x plus d x x n l, right? x n k in this, so d x n k x is less than epsilon by 2. Similarly, this is also less than epsilon by 2. Okay, so less than epsilon. But just we got at the top of this page that dxn kxnl greater equal to epsilon. Here we are getting less than epsilon. Okay, which contradicts the fact that dxnk xnl greater equal to epsilon. Okay, so this is an open ball centered at x which can contain only one, at most one term of this. All other will be outside of this. So this subsequence cannot converge to x. Okay, so this x and k cannot converge to x. Okay, or you can say we assuming that this x and k is convergent, we arrive at a contradiction. Okay, so it cannot be a convergent sequence. Okay, so, or you can say x is arbitrary in this. Okay, so whenever we are taking a point from this metric space, we see that x and k is not converging to this x. So ultimately x and k is not convergent. Okay, so this x and k, this subsequence is not convergent. Now this subsequence also an arbitrary subsequence of the sequence xn. Look at this. Here we have taken at the end of the earlier page. Let xn k be any subsequence of xn, and we see that this xn k is not convergent. What does it mean? We see that this xn k is not convergent, but xn k any subsequence of xn. So whenever we are taking a subsequence of xn, we see that it is not convergent. So xn has no convergent subsequence. Okay, since x and k is arbitrary subsequence of xn. Okay, so xn has no convergent subsequence. Fine. Okay, now what is xn? What is xn? Look at this, the earlier page. xn is a sequence in the metric space xd. Okay, xn is a sequence in the metric space xd, but xd is sequentially compact. Okay, so in a sequentially compact metric space, xn is a sequence having no convergent subsequence. So this contradicts the fact that, okay, so this contradicts the fact that the metric space xd is sequentially compact. Okay, so ultimately, if we assume that xd not totally bounded, we arrive at a contradiction. Hence xd must be okay, totally bounded. Okay, so in this part we have shown that if a metric space is sequentially compact, then it is complete and totally bounded. Completeness is here and totally bounded. Now we will show if a metric space is complete and totally bounded, then it is sequentially compact. Okay, this proof also very interesting. Okay, fine. Okay, so now let me prove the converse part, where we will assume that the space is complete, that is every Cauchy sequence therein is convergent, and it is totally bounded, and we will show it is sequentially compact. So conversely, converse part is let xd be complete and totally bounded. Complete and totally bounded. We will show it is sequentially compact. So we have to start with any sequence in this metric space, and finally using this completeness and totally boundedness, we have to find a convergence of sequence of it, isn't it? Okay, so let xn be any sequence. This be any sequence in this metric space HD. Okay, any sequence HD. First we'll use the total boundedness. Okay, since HD is totally bounded, so for every epsilon greater than 0, epsilon net of this x will exist. That is, there will be finite number of points. Okay, so that the open balls centered at those points, each having radius epsilon, will cover whole x, isn't it? Okay, and this will hold for any epsilon. That is, for every epsilon we will get a finite number of points. Okay, now okay, so this any sequence in this. Okay, since HD is totally bounded, since it is totally bounded, okay, so epsilon net for x exists for every epsilon greater than 0. So in particular, if I take epsilon equal to half, then that half net will exist. Okay, so let epsilon equal to half, so half net will exist. What does it mean? It means there will be finite number of open balls, each having radius half, that will cover whole x. That will cover whole x, and this is a sequence in x d. So that finite number of open balls is having radius half will contain all the terms of this sequence, but there are infinitely many terms of this sequence, isn't it? So there will be at least one open ball having radius half, which contain, okay, let me write. Then there is one open ball of radius, right, of radius half, that will contain infinitely many terms, many terms of this sequence xn. Okay, and that infinitely many terms will constitute a subsequence of this xn. Okay, so let xn1 this be the corresponding subsequence of the sequence xn, which is totally confined within that open ball of radius half. So all the terms of this subsequence of xn confined within an open ball of radius half. So diameter 1, isn't it? So distance between any two terms of this subsequence is less than 1, isn't it? Okay, so dx say k1 and dxl1, here n varies, so k1 and l1 is less than 1, isn't it, for all kl in n. Okay, again let epsilon equal to 1 by 2 square. Okay, then also an epsilon net for x exists. Okay, so there will be finite number of open balls, each having radius 1 by 2 square, which cover whole x. So it will cover this subsequence also. Okay, but there are finitely many open balls, but this subsequence has infinitely many terms. Okay, so one of those finitely many open balls, each of radius 1 by 2 square, will contain infinitely many terms of this subsequence, isn't it? So there exists an open ball of radius 1 by 2 square that contains infinitely many terms of this subsequence xn1, isn't it? and these infinitely many terms will form a subsequence of this subsequence. That is, that infinitely many terms will be again a subsequence of the main sequence xn, isn't it? Continue. Okay, so let this xn2, this be the corresponding to this infinitely many terms of this, okay, be the corresponding subsequence of this subsequence xn1, okay, which totally confined within that open ball of radius 1 by 2 square. So in this case, now this is open ball of radius 1 by 2 square, so diameter is half, 2 into, and within this all the terms of this subsequence xn2, okay, are confined. So the distance between any two terms of this subsequence xn2 will be less than half, okay. So dx, again say k2 xl2, this is less than half for all k l in set of natural numbers. So here d x k1, the first subsequence, okay, terms of the first subsequence is less than 1. Here distance between any two terms of the second subsequence, okay, in some sense the less than 1 by 2. So when this is 2 to the power, okay, let me come to the main point. So in this way one will get a subsequence in general xnm of xn of xn, such that here n varies, okay, in the, this is the mth subsequence, okay, xn1 is the first subsequence of xn, then xn2 being a subsequence of xn1, it is also a subsequence of xn, so it is the second subsequence of xn. Let me say like this, okay, so xnm is the mth subsequence of xn, fine, okay, n varies, such that what we will get as simple as that d x km xlm, it will be less than, okay, less than 1 by 2 to the power this minus 1, here 1, so 2 to the power 1 minus 1, that is 2 to the power 0, so 1 by 1 1, so here it is 2, so 2 to the power 2 minus 1, so here m, so m minus 1. Now one more inequality is there, it is very easy. let me draw this in another page. Okay, look at this. Okay, we have seen that the first subsequence is xn1, that is this xn1. All the terms of this subsequence of xn confined within open ball of radius half. Open ball of radius half. That is their distance of diameter actually 1. Fine. Okay, so distance between any two members of this is 1. So let me write this 1. Then we got xn2, and all the terms of this subsequence confined within an open ball of radius 1 by 2 square. So distance between any two members of this is half. We have seen this is half. Okay, similarly in case of xn3, the distance between any two terms of this sequence is less than 1 by 2 to the power this 3 minus 1, just 2. Okay, m minus 1 in this way. Okay, now distance between a term of this sequence and a term of this sequence will be less than half, because terms of this sequence also in this, terms of this sequence also terms of this, because this is subsequence of this. So if we take a term from this and a term from this, so we can consider them as two terms of this. So it will be, their distance will be less than half. Okay, the minimum, the 2 to the power minimum minus 1. Okay, such that this, so and dx, okay, so dx say km and dx ln, this will be less than if n is the minimum, if m greater or equal to n. Okay, then it will be 1 by 2 to the power the smaller one, that is n minus 1, as I explained here, isn't it? This in particular, this is important. Okay, in particular d x mm comma x nn, nn, this is mth, the term of the mth subsequence, and this is term of the nth subsequence. So if m is greater than n, so n appears before m, so it will be also like this, 1 by 2 to the power n minus 1, isn't it? Very simple calculation. Okay, minded this. So we almost done. How? Just few lines. Wait. Okay, look at this. So let us concentrate. Okay, we got this xn1. This is subsequence. So the terms are x 1 x 2 1 x n varies, x 3 1 x 4 1 dot dot dot. Then we got x and 2. Here also n varies, no? So x 1 2 x 2 2 x 3 2 x 4 2 dot. Then x in 3. Okay, so x 1 3 x 2 3 x 3 3 x 4 3 dot, 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 dot. Now let me consider this. Okay, so all are subsequence of xn. This is a subsequence of xn. This is also a subsequence. If we consider this, no, this will also be a subsequence of xn. All are coming from this xn. So let us concentrate with this subsequence, to this subsequence. Okay, fine. So let us focus to this subsequence xmm. Okay, which is a subsequence of the main sequence xn, such that dxmm and xnn, it is less than 1 by 2 to the power n minus 1 if m is greater or equal to n. Okay, so dxmm xnn less than 1 by 2 to the power n minus 1. So if n tends to infinity, then m also tends to infinity. That is, when mn tends to infinity, we see that this tends to 0. Okay, so it is a Cauchy sequence, but this is not the logic. Okay, I will explain later on. Okay, okay, so dxm xnn, this is 1 by 2 to the power n minus 1 if m greater or equal to n. And from this you can show, this implies actually this x m is, or nn is a Cauchy sequence, in the metric space xt. Okay, since this metric space xt is complete, here is the place where we are using the completeness of xt. Okay, we assume that the metric space is complete and totally bounded. Okay, so far we have used totally boundedness. Now this is the place where I am using completeness. Since this is complete, so every Cauchy sequence is convergent. So xnn being Cauchy, so it is convergent. So xnn is convergent. Okay, so every sequence xn, we have taken any sequence xn in hd. So every sequence xn in hd has a convergent subsequence. This xnn has a convergent subsequence. Okay, subsequence in hd. So hd is complete. So HD is sequentially compact. Okay, and we are done. Isn't it? So this part also complete. The converse part also done. In this part, we have assumed that the metric space is complete and totally bounded, and we wanted to show that it is sequentially compact, and it is shown it is sequentially compact. So we have done. So in a metric space is sequentially compact if and only if it is complete and totally bounded. So after proving this and after introducing these two new concepts, Lebesgue numbers and net, epsilon net, totally boundedness, we are now in a position to prove the main theorem that in case of metric spaces, sequential compactness, classical compactness, countable compactness, and limit point compactness, these four kind of compactness are equivalent. So keep watching, we will prove it in the next clip. Thank you.